So in a previous video on scatter plots, I asked you, or showed you how to construct a scatter plot and then to visually inspect the scatter plot and try to determine if there is an association, whether it's positive or negative, and if there's any kind of a pattern, linear, nonlinear, no pattern. A visual inspection could lead to different conclusions from two different analysts because it's somewhat subjective. So is this linear? Is it nonlinear? So next we're going to look at something called the correlation coefficient. And we use the symbol R for the correlation coefficient. So the correlation coefficient is a measure of the direction and strength of a linear relation. So the formula for calculating R is rather complicated, and so I'm not going to bother with that in this video. Rather, I'm going to show you how to calculate the correlation coefficient with a TI-84 and then how to interpret the result. So some things to know about R. Firstly, R is always going to be a value between -1 and +1. And so let's look at what different values of R might indicate. So I'm drawing a segment, a line segment that extends from -1 to +1, and right here in the middle I'm going to put 0. So a correlation coefficient of -1 would represent a perfect negative linear relationship. So this is perfect negative linear relationship. On the other hand, if we have a value of 1 for the correlation coefficient, you may guess that that indicates a perfect positive linear relationship. So perfect positive linear relationship. And notice that here, well, my intention was for these to fall perfectly on a straight line with a positive slope, whereas these fall perfectly on a line with a negative slope. Now, in the middle here we have 0, and I want to be very careful with how we interpret this. This could mean that there is no pattern at all. So in this case we would expect a R value of 0. But be careful, because you may have a pattern that is nonlinear, but a pattern nonetheless, and you could still have a value of 0 for R, because this is a measure of the strength of a linear relationship only. It will not tell us whether or not there's, for instance, a quadratic relation. So it's easy to interpret -1, 0, and 1, but this is a real number line, and there are an infinite number of values between -1 and +1. So let me give you a couple more examples. So maybe we would have not a perfect negative linear relation, but a strong negative linear relation. And so these don't line up perfectly, but there is maybe instead of a single line, maybe there's a band so that would capture most or all of these data points. In this case, you might have an R. It's still going to be negative, but maybe it would be -0.9. So it's not perfect, but it's close. And then, somewhere going a little bit between there and 0, things could get a little bit more random. So you would have to use a little bit more imagination or a wider band to capture things, but there's still a general trend. Just need a wider band, and maybe this would be R of -0.7. On the other side, let's see, maybe you would have things that line up somewhat, so a loose pattern, and then there are a few values that are off. So maybe this guy down here, and maybe there's another one up here. They don't quite fit the pattern. That will weaken the linear relation. And so this might be an R of 0.5 or something. And then as we get to a little bit more in order here, so maybe this is R of 0.8. So the closer you are to either extreme, -1 or +1, the better your points will line up. In the middle, where R is 0, you could either have no pattern or perhaps a pattern, but just not one that is not linear. Now, that gives us, there's still some ambiguity here. We want to know where's the line that separates nonlinear from linear. Well, this is the problem is that this is a moving target. That line that separates the nonlinear from linear on this scale, even just between 0 and 1. We will have to use a table to look up a cutoff point that we'll use to determine whether our sample is indicative of a linear relationship or not. So let me show you what this table will look like, and then explain how it works. So here's an example of a table where these are called critical values, the values that we find here in the table. In the leftmost column, we see these are values for n. This would be a sample size. The smallest sample size that's would be here in this table would be a sample size of 4, and they go up, to 92, and there's a jump to 102. Now, in the small data set that I was using for an example, I had 6 ordered pairs that we plotted in our scatter plot, and I see 2 critical values here in the 6th row, 0.811 and 0.917. If I have a value of R that's greater than either one of these, I will say that that is indicative of a linear relation. Now, the difference between the two, if I choose the smaller value, in this case 0.811, there's a 5% chance that I could draw the wrong conclusion. I could end up saying there is a linear relationship based on my sample, when in fact there is not a linear relation in the population. There would be a 5% chance of me making that mistake if I use this critical value. If I choose 0.917 as my cutoff point, then there's only a 1% chance that I would make that mistake of saying there is a linear relation when there's not. So this is a stricter standard, and it has a lower chance of that type of mistake where I say there is a relation, a linear relation, when there's not. So let's go to our calculator, and I'm going to take the example that I used in the previous video, and we're actually going to calculate the correlation coefficient and then compare it to the values in this table to say if there is evidence of a linear relation. So here's my TI-84. I'll turn it on, and I'm going to go to my stat menu. It's under the edit feature. I'm going to clear these lists. I'm moving my cursor to the column header and then hitting clear and enter. And then let's enter our data 1, 6, 4, 3, 7, and 2. And for the y values, 2, 5, 5, 3, 3, 4, and 1. So first let's look at the scatter plot while we're here. I'll hit zoom and then choose option 9, and here's the scatter plot. I'm going to just turn something off here, clear, go back to the scatter plot. Alright, so this is what we saw in my hand drawing. So now I'm going to show you how to get the correlation coefficient. So we're going to again go to the stat menu and scroll over to the calculations menu. And I'm going to choose the 4th option. It's linear regression. You may have prompts that say, where is your x variable, where is your y value. I don't have that. This is an older version of the TI-84, so I have to manually put those in. I'm going to use my second key and then hit 1, and L1 will pop up, and then I'll use a comma and then indicate list 2. This is the location of my x values. This is the location of my y values. I can hit enter, And the R value that I'm getting is the last thing here. It's 0.85. So I'll make a note. R is 0.854, and then I'll just stop at 4 decimal places. 8547. Let's see. Does that provide evidence of a linear relation? So let's look again. My critical values, remember these are the values that are in the table here, in the 6th row are 0.811 and 0.917. 0.811 and 0.917. So my correlation coefficient R is greater than the critical value for, I'm going to point out again where I'm getting this. The 0.81, that alpha is called the level of significance, and again, this is the chance that you will say there's not a linear, there is a linear relation when there's not. So if I am going to be happy with a 5% chance of it happening, I can use this critical value. But if that is too loose, that's too much risk, I can only accept a 1% chance of making a mistake, then I'll use this critical value. So notice that my R is greater than 0.811. So I could say that there is evidence of a linear correlation. However, I would either note to myself, or I may have to disclose this to whomever I'm reporting to, and say that there's a 5% chance that I'm wrong here, and that there is not a linear correlation in the population. So I was drawing that conclusion based on a relatively small sample, so that my conclusions could be wrong just by the nature of sampling. So lastly, I want to show you a couple of other things that were in this output from the calculator. I have this y equals ax plus b. Now, oftentimes, we are used to saying y equals mx plus b, where m is slope and b is y-intercept. Your calculator is using ax plus b. So a is the slope and b is the y-intercept. So the values that I'm getting here are a is 0.52 and b is 1, and I'm just rounding it 2 decimal places. So the line y equals 0.52x plus 1, this is called the regression line. And so this is a line that approximates the pattern in my scatter plot. And so it's the line basically, right here. Now I know that the line that best fits my data is the line y equals 0.52x plus 1. And again, that comes from this calculator, and it was based on the information that was in my list. And if you want to add that to your scatter plot, I can go to my function list, so that hitting that y equals button and say 0.52, use my variable key, plus 1, go back to my scatter plot by hitting the zoom key and then 9, and now I can add that regression line. And you'll see it doesn't hit every point. It comes really close to this 4th point. And so it's not a perfect linear relation, and I knew that the correlation coefficient was 0.85. If I saw every point on the line, that would be perfection, and I would expect a value of +1 since I'm seeing this upward trend. So in the next video, I'll show you a real-world application of this from start to finish. So I hope you'll tune in.